In this problem, we count the number of different 10-bit bit strings that have exactly 2 ones in the first half and exactly 1 1 in the second half. So again, we have 10-bit bit strings. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right, this is the first half. This is the second half over here. So over here in the first half, right, we have 2 ones. So there's many possible ways we could do this. We could put 2 ones there, and then it would be like that, right? We could do the 2 ones there, and then the zeros would go there. So for the first half, right, we have 5 positions. We have 5 positions. Choose 2 of them to be ones. And for the second half, right, it's 1 1 in the second half. So wherever you put it, like that. So we have 5 positions. Choose 1 of them to be a 1 for the second half. All right, now as an aside, I noticed that this number 5 choose 1, this is going to be 5. And if you look at this, you think about where could you put these ones. You could put the 1 there, and then those would all be zeros, right? Or you could put it there, and then you'd have all zero like that. So there's 1, 2, 3, 4, 5 different places you could put the 1, then everything else is determined. That's another way to see that 5 choose 1, it has to be 5. Okay, but anyway, that's not necessarily the point. Okay, so we have 5 choose 1 there. All right, so then the total number of different ways that, or the total number of 10-bit bit strings that have exactly 2 ones in the first half and exactly 1 in the second half is the number of ways that you can distribute 2 ones to 5 positions multiplied by the number of ways that you can distribute 1 1 to 5 positions and then have zeros everywhere else. All right, and so we're using the product rule for counting here to multiply these two in choose R computations. And now why now you might think, okay, why are you multiplying them? All right, so the number, so we have all of these, so first we have all of these positions, right? We have all of these positions, but you can think of the first half as 1 position where there's, within that 1 position, there is 5 positions that you can choose 2 of them to be 1s, and then this is a whole nother position. The second half is another position. And notice that however you choose to distribute the 1s in the first half has no bearing on how you choose to distribute the 1s in the second half. So there's independence there. And so then we can multiply. 5 choose 2 times 5 choose 1. That'll be our answer. Now if you wanted to, if you want to put as your answer 5 choose 2 times 5 choose 1, that's perfectly fine. I just want to illustrate now that this is something we could compute relatively easily without even having to go to that formula. 5 choose 2, remember, this is like you have, let's say, 1, 2, 3, 4, 5. You have these 5 nodes, and we draw edges between them to indicate that they're in the same set. So we have a set with 5 elements, 1, 2, 3, 4, 5, and you go like this, right? Something like that. Let's see, did I get 1 and 3? And then, so blah, blah, blah. Okay, 1 and 3, and then 4 and 5 or something. There would be your graph there. You count the number of edges there. Remember that when we did that, right, we figured out that anything choose 2, so this is going to be 5 times 4 over 2. And then remember, 5 choose 1, this is always 5. So if you didn't understand what I just did there with the graph and all that, it doesn't matter. We'll see more of that as we go, but one thing that you may want to memorize is that n choose 2 is equal to n times n minus 1 over 2. That'll just make your life simpler, and that n choose 1 is equal to n. Right, so 5 choose 2 is 5 times 4 over 2, and 5 choose 1 is 5. Let's see, now we can do some math there. 2. So 5 times 5 is 25. 25 times 2 is 50. So the answer is 50. You could also write the answer just like that.